Hello, my name is Nathaniel Acosta, and this is Lab 3 Gravitational Motion. So to start, the purpose of this lab was to demonstrate gravitation along multiple objects as well as circular motion mechanics. To model it, we used two different glow script simulations. Physics principles that are in this lab are Newton's second law, gravity principles, and curving motion principles. And a quick preview of the results of this lab is that gravitational motion can often be simulated by using curving motion to find things such as the force of the system, and in this case allowed us to demonstrate a dynamic system of multiple gravitational bodies. So for part 1 of the lab, we have we can make some assumptions about the system. First is that the system is the star and the surroundings are the black hole. The planet and black hole both have a constant mass, and the origin of the coordinate system is the black hole. The planet also has some initial velocity to ensure that it enters an orbit around the black hole instead of just falling inwards. So this is the part 1 simulation. Our initial conditions is that our delta t is 60 seconds, and the experiment takes place in 1 full day, which is 86,400 seconds. The start mass is 2 to the 30, and our net force is just the gravity from the black hole. As you can see, this is the output of the simulation in this bottom picture, and this is the black hole and the sun in a somewhat elliptical orbit around the black hole. So as you can see here, it's going to start speeding up around this part of the curve until it enters here, and it enters its slowest and then goes back to here. From the final conditions of the simulation, the black hole mass is approximately 9.47 times e to the 33, which is averaged out from the mass printed out using the gravitation formula each 60 seconds. The reason why I had to use the average will be covered later in the possible errors. The star mass is still constant, so 2 times e to the 30, and the F-net is still the gravity force from the black hole. On the right, this is the calculations that I used to find the velocity, the perpendicular parallel force, and everything for the star. Next, on to part 2, we can make a similar system and assumptions. The first is that the system is our ship, and the surroundings are the planet and the moon. And the goal of the simulation is to sustain a figure 8 trajectory around both the planet and the moon. The moon and ship also have some initial velocity, much like System 1, in order to prevent them from crashing into the planet, and the origin of the coordinate system is the planet. So the initial conditions of the second simulation is that our delta t is the same at 60 seconds. However, this time the experiment takes place in 1 month to allow for the orbit to saturate and see what the pattern looks like. Our ship mass is 7 times e to the 12th, moon mass is 6e to the 25th, and planet mass is 8e to the 27th. All of these are constant, and our F-net on the ship is going to be the force of gravity from the planet and the force of gravity from the moon. And our initial ship velocity is 1.8 e to the 4th, 2.46 e to the 4th. And this is obtained from a guess and check method where it is plugged in and just seeing how it works. So our final conditions is that the ship is in a circular orbit around the moon and the planet as well. So as you can see, it enters almost a helical pattern circling around the moon and then also around the planet. Because the planet has no z difference and they're all lying on the same z-plane, the motion is strictly in 2D, so only x and y. But the F-net is still the force of gravity from the planet and the moon. And there was no crashing during the entire month designated time period. On the right here, this is my calculations for the force of gravity from the moon and the planet on the ship. And we also used Newton's second law to calculate the position and velocity and make sure that the diagram actually moves. So for the overall conclusion, so for part 1, the gravitational forces perpendicular and parallel component allowed us to correct an average mass of the black hole from just the velocity and mass of the star as well as the position of the star. For part 2, the ship was able to obtain an orbit around both the moon and the planet with its initial velocity. There are some possible errors in the lab. For part 2, due to the guess and check nature of the initial velocity, like I said before, the velocity is not exactly correct to obtain a figure 8 orbit. Just on the right, this is from 5 different delta t's, and it ranges all the way from like 9.7 to 9.4, which is quite a range for mass. Also, the mass of the black hole changes with the formula obtained. Sorry, that was this part. And then due to the guess and check nature of the initial velocity for part 2, velocity is not exactly correct. There's a wider range of successful values without crashing into the planet or the star. So for what does it mean? Although the dp and dt, the change of momentum over the time, and F-net were the same value-wise, they were found in two different ways. The dp dt only the mass and the velocity of the ship, while the FNet needed the gravitational forces of the moon and planet on the ship, which you could see from our calculations. And if we wanted to predict motion of the entire system, you would have to make sure that there are no close celestial bodies that could also interact with the system, and that the system would also most likely move in terms of the origin, as a black hole or planet would no longer be the origin. Instead, the entire system would move away from it most likely. However, the most dominant interaction would be everything orbiting around the black hole due to the much larger mass of the black hole. And that is it.